In this lesson, we are going to learn how to apply what we've learned about exponential functions and their formulas and actually create explicit formulas from either word problems or graphs. So let's look at these two examples that I have right now. I can tell that they're continuous graphs, so I know that I'm going to use my exponential formula, which is going to be f of x equals ab to the power of x. And they give it to you in there just in case you don't know it. Let's look at sample C. In example C, we have 2 points. That's all we are given. So the first thing that I like to do when I have that is I like to create a table with x and y values. I'm going to go ahead and plug in the values that I have for x and y based on the points that my graph is giving me. Once I have my points, I can identify my initial value here. This graph starts with x equals -2, and then it goes up to the y-intercept, which is 2. However, my initial value is always talking about and referring to what happens when x is 0. So in this case, my initial value is not going to be the first one. It is going to be when x equals 0, which in this case is 2. So a is 2. Now I have to figure out what b is. So your common ratio is the scale at which your y values are growing. But in order to figure that out, you have to first make sure that your x values are increasing by 1. Because if you don't have continuous points, then the scale factor that you're going to get for your y values is going to be over or underestimated. So what you want to make sure is that you go by ones. So in this case, our points do not go by 1. So we have to figure out what the values might be. So in this case, I am trying to figure out what y is when x is -1, or I could also figure out what y is when x is 1. But in this case, it was easier for me to find out what y is when x is -1, in which in this case, y would be 1. So once I have that, I'm essentially looking for a scale factor. So basically, the previous y, 0.5, to get to from 0.5 to a 1, what is the scale factor I'm multiplying that by? And of course, if I write an equation for that, then I can easily solve for it. And I notice that b is going to be 2. So the scale factor is going to be 2. And then I have everything I need to fill in my formula. My equation is then g of x equals 2 times 2 to the power of x. Let's move on to the next example here. We have our points. But right away, I can tell that my x's are going by 2. They're not going by continuous points, one by one. So I'm going to go ahead and just try to figure out what the value of y is when x equals 1. And that way, I'm going to have continuous points. X equals 1 and x equals 2. So I realize that from the graph, when x equals 1, my y is going to be 4.5. And so I can determine the scale factor then, because from 4.5 to 27/4, my scale factor is going to be 1.5, so my common ratio in this equation is going to be 1.5. And that's an easy way to do that. So I have everything I need. B is going to be 1.5. A, my initial value, when x equals 0, in this case, is going to be, I'm looking at the graph, and it looks like A is going to be 3. So my equation is going to be 3 times 1.5 to the power of x. So that's a mistake I'm making there, to the power of x. Now sometimes you can also write this as a fraction. One of the things that I love most about algebra is that it becomes increasingly useful in life, and we can apply algebraic models to situations. Let's look at this example right now. We have a problem where they want us to find a model that predicts the state population of California. And so right away I can tell it's continuous. If you remember back from our bacteria example, when things grow, they grow in a continuous manner. They don't grow in a discrete manner. So I know I'm going to use an exponential function. I'm going to set up my table. I have 2 values here. I have the year 1900. The population at that time was in thousands, 1,490. And then I also have the year 1920. The population at that time was 3,554. And so what this problem wants me to do is it wants me to create both a linear and an exponential function to determine which one is better. I actually have the census population data, and we're going to compare and see which model would be the best fit for this particular problem based on the data that we have collected. And then we're going to use that model to predict it in future years for the ones that we don't have census information for. So let's get started. Your linear equation, we know that the formula for that is y equals mx plus b, and we know that your exponential equation is y equals ab to the power of x. So we first have to figure out our linear equation. Let's look at trying to figure out our slope. We need our slope and we need our y-intercept. So when we think about figuring out the slope, we have to figure out the change in y values over the change of x values. In this case, rise over run. So let's go ahead and do that. So after we do the math, we figure out that our slope is going to be 103.2. And our y-intercept in this case, since we don't know when x is 0, so like the year 0, we don't really have data for that population. We're going to use the year 1900 as our y-axis as the 0. And in that case, then our y-intercept would be 1490. And so when we plug those numbers in, then we are going to have our equation y equals 103.4, and actually I'm going to use function notation, so it should be f of t, t being time, equals 103.2 t plus 1490. Now let's go ahead and figure out our exponential model. That's our linear model. For our exponential model, we're going to have to come up with our initial value, which is a. In this case, it's 1490. Then we have to come up with our common ratio. So this is going to be really difficult to do for this. I'm going to show you a way to do it with a calculator. But for now, I'm just going to give it to you. And then in our next video, I'll show you exactly how I came up with this. B is going to be 1.044. So my formula then is 1490 times 1.044 to the power of t. So then I'm going to go ahead and on the first column, plug in numbers for t. So each year I'm going to plug in the t value and then come up, do the math and get the y values. And then on the middle column, I'm going to come up with the g values for the exponential function. And based on this, what I'm seeing is that for the year 1937, my exponential function became closest. For the year 1960, my exponential function was closest. For the year 2010, neither of them was actually close. So just because 2 out of 3 years came the closest to the exponential function, the best mathematical model to use for this particular problem would be my exponential function. So if I were to predict, I would probably use the exponential formula instead of the linear one because that's a better model for it.